Hello there, and welcome to the Sleepy Science Channel. Tonight, we're drifting far beyond the edges of galaxies into the vast and mysterious realm of intergalactic space. This is not the empty darkness we once imagined. It is a hidden expanse where invisible matter drifts between colossal structures, where ancient light travels for millions of years without interruption, and where entire galaxies move like distant ships across a cosmic ocean. Between them lies a landscape so immense that even our imagination begins to falter, shaped by forces we are only just beginning to understand. Out here, stars can wander alone, far from any home. Entire galaxies can be stretched, torn, and remade. And woven through it all is a vast, delicate structure that connects everything, a cosmic web that defines the architecture of the universe itself. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your eyes to grow heavy. And let your mind begin to gently unwind as we explore the vast expanse between galaxies together. Let's begin. Intergalactic space is not empty. It is filled with ghostly matter. For a long time, people imagined the space between galaxies as a pure black vacuum, almost like a blank page between chapters. But it is not blank at all. That darkness is threaded with thin gas, scattered atoms, magnetic fields, and drifting particles that are almost impossible to notice unless you know exactly how to look. In some regions, a single cubic meter holds less matter than the best vacuum chambers on Earth. Yet across the scale of the universe, that faint material adds up to something enormous. It forms a hidden environment that galaxies move through and feed from. It can be heated by violent events, stirred by gravity, and lit for a moment by distant quasars. So when you picture the universe, it helps to stop imagining islands floating in nothing. The space between those islands is a real place with substance, history, and a strange, almost invisible presence of its own. Most normal matter may hide between galaxies, not inside them. One of the strangest discoveries in modern astronomy is that stars, planets, moons, and people make up only a small fraction of ordinary matter. For years, astronomers kept coming up short. The numbers from the early universe said more normal matter should exist, but when they counted galaxies, too much of it seemed to be missing. The answer appears to be that it was never truly gone. Much of it was spread out beyond galaxies in a vast, thin medium that is hard to detect. It is not dark matter, and it is not mysterious in composition. It is the same kind of matter that builds everything familiar, mostly hydrogen and helium, stretched so thin that it nearly vanishes from sight. That means the brilliant parts of the cosmos are not the whole story. Much of the ordinary universe may be hiding in the dim reaches between galaxies, where almost nothing seems to be there at all. Galaxies drift through vast cosmic oceans of thin, superheated gas. A galaxy does not simply hang in stillness like a painting on a wall. It travels through an environment, and in galaxy groups and clusters, that environment can be immense clouds of gas heated to extraordinary temperatures. This gas is so hot that atoms are stripped apart into plasma, reaching millions of degrees while remaining incredibly thin. If you were there, you would not feel a furnace pressing against you. You would feel almost nothing because the particles are spread so widely apart. Yet over colossal distances, this blazing medium becomes one of the largest visible ingredients in a cluster. Galaxies move through it the way ships move through water, though far more slowly and with far stranger consequences. Gas can be peeled from them. Their future star formation can be altered. Their shapes can change. So the next time you imagine a galaxy crossing space, picture it not as drifting through emptiness, but as sailing through a nearly invisible, superheated sea. The universe is woven into a colossal web between galaxies. On the largest scales we can map, the universe does not look random. It looks structured, almost eerily so. Galaxies gather along enormous filaments that stretch across space like luminous threads, while between them lie vast, emptier regions called voids. The result is something astronomers call the cosmic web. It is one of the most astonishing patterns in nature. Matter did not spread out evenly after the early universe. Tiny ripples in density grew over time under gravity, drawing gas and galaxies into long connected strands. Galaxy clusters formed where several of these strands meet, like bright cities at the junctions of immense roads. This means intergalactic space is not just the gap between objects. It is part of the architecture itself. The grand design of the cosmos is written there. When astronomers map the universe, they are not simply plotting isolated galaxies. They are uncovering a deep structure that links them across distances almost beyond comprehension. Some intergalactic voids are so huge they dwarf galaxy clusters. If the cosmic web is the grand framework of the universe, then voids are its great silent chambers. These are not little gaps. Some are so vast that they stretch across hundreds of millions of light years. A galaxy cluster might seem unimaginably large to us, yet a single void can make even a cluster look small by comparison. Inside these regions, galaxies are rare and matter is unusually sparse. They are among the emptiest places known. What makes them so fascinating is that they reveal shape by absence. Just as the dark spaces in a stained glass window help define the pattern, these enormous hollows help show us how the universe is arranged. They also raise deep questions about how galaxies form when the surrounding environment is so thin and quiet. In a universe famous for its stars and fireworks, voids are a reminder that scale can be most astonishing where there is almost nothing to see and almost nowhere to hide. Light can cross intergalactic space for millions of years uninterrupted. When you see a distant galaxy, the light reaching your eyes has survived a journey that feels almost impossible to imagine. It may have left its source before early humans existed, then crossed the gulf between galaxies for millions of years without striking anything important enough to stop it. That journey is possible because space is so thin. Even though intergalactic regions contain matter, they are sparse enough that a photon can travel for extraordinary distances almost unbothered. It is as if a single note from a distant bell were allowed to ring across an entire ocean of darkness and still arrive intact. This is one reason astronomy works at all. The universe is transparent enough for ancient light to reach us. Every telescope depends on that long survival. And there is something beautiful in it too. The cosmos is so large and so empty that a tiny packet of light can cross the darkness for ages, carrying a message from another galaxy into view. The space between galaxies preserves some of the universe's oldest clues. Some places are valuable because they are busy. Others are valuable because they are undisturbed. Intergalactic space often belongs to the second kind. Away from the crowded interiors of galaxies, matter can preserve traces of much earlier cosmic times. Thin hydrogen gas still carries information about how the universe changed after its first stars and galaxies lit up. Ancient patterns remain imprinted in the way light passes through that gas. Astronomers study these faint signals to reconstruct lost chapters of cosmic history, including when the early universe emerged from its murky youth into clarity. In a sense, the space between galaxies acts like a deep archive. It is less cluttered by later local events, so some older fingerprints remain easier to read. That makes these regions more than empty stretches. They are a record of transformation on the biggest scale imaginable. The darkness between galaxies can tell us what the younger universe was like long before familiar galaxies fully matured. Galaxies can steal gas, stars, and even worlds from one another. Gravity is not polite on cosmic scales. When galaxies pass near each other, they do not simply exchange glances and move on. They pull, stretch, and disturb one another with enormous force. Gas can be stripped out into long tails. Stars can be tugged away and thrown into new orbits. Smaller galaxies can be partially dismantled by larger neighbors, losing the raw material they needed for future growth. In extreme cases, entire star systems may be carried along in the chaos, meaning planets could find themselves pulled into a completely different galactic environment than the one where they formed. These events unfold over immense spans of time, so they do not resemble sudden collisions in the ordinary sense. They are more like cosmic theft carried out by slow, relentless tidal forces. The result can be beautiful from afar, with bridges and tails of light stretching between galaxies. But behind that beauty is a fierce truth. Even galaxies can prey upon each other. Even empty intergalactic space can burn at millions of degrees. This sounds impossible at first. How can something nearly empty also be unimaginably hot? The answer lies in what temperature really means. It measures how fast particles are moving, not how crowded they are. In intergalactic space, particles can be extremely sparse and still carry enormous energy. Gas between galaxies is often heated by shock waves from cluster mergers, by matter falling into deep gravitational wells, or by outbursts from supermassive black holes. That can drive temperatures into the millions of degrees. Yet because the gas is so thin, it would not feel like standing inside a furnace. There is simply not enough material there to transfer heat, the way air or fire does on Earth. This is one of the great alien qualities of the universe. The familiar rules of daily life stop being intuitive. A place can be dark, thin, almost empty, and still be a realm of astonishing thermal violence, glowing invisibly in high-energy light we cannot see with human eyes. Our own galaxy is sailing through intergalactic space right now. It is easy to think of the Milky Way as fixed, like a backdrop we live inside. But it is moving. Our galaxy travels through the wider environment of the local group, while gravity links it to Andromeda, smaller companions, and the larger structures beyond. The Sun, the Earth, and everyone who has ever lived are being carried along on that journey without feeling the slightest motion. At the same time, the Milky Way rotates internally. Stars orbit within it, and the whole group is responding to even larger gravitational pulls in the cosmic landscape. So our situation is much stranger than it seems. We are not resting in a stationary island. We are passengers inside a moving galaxy, crossing a region of space that extends far beyond our own stellar home. That thought changes the sky a little. The night above us is not a painted dome. It is part of a voyage already underway, through a realm so vast we are only beginning to understand it. The Milky Way lives inside a crowded galactic family called the local group. Our galaxy is not alone in the dark. It belongs to a small but busy community called the local group, a gravitational gathering of more than 50 known galaxies spread across millions of light years. The two giants are the Milky Way and Andromeda, with Triangulum following behind, while dozens of smaller companions circle them like persistent attendants. Some are bright enough to stand out. Others are faint dwarf galaxies that look more like smudges than star cities. Yet all of them are bound together by gravity, moving through the same broad region of space in a long, slow cosmic dance. This means that when we look beyond our own stars, we are already in a neighborhood with structure, relationships, and history. The Milky Way is not an isolated kingdom. It is one large member of a local family. sharing space with companions, rivals, and future merger partners inside a region that is far more crowded than it first appears. Andromeda is the nearest great galaxy across intergalactic dark. If you step outside on a truly dark night, there is a chance you can see another galaxy with your own eyes. Not as a spiral of stars, of course, but as a faint, misty patch. That blur is Andromeda, the nearest large galaxy to our own, and the most distant object most people will ever see without a telescope. Its light has been traveling for more than 2 million years to arrive at Earth, which means you are seeing it as it existed long before humans built cities or wrote history. It contains perhaps 1 trillion stars and stretches far wider than the Milky Way, though distance makes it seem delicate and small. What gives it special power in the imagination is its nearness. Across the immense dark between galaxies, there is another great island of stars close enough to glimpse unaided. That sight turns intergalactic space into something real. Beyond our galaxy, another one is already waiting in view. Dwarf galaxies drift around giants like moths around lanterns. Large galaxies rarely travel alone. Around them gather smaller companions called dwarf galaxies, faint systems that can contain anywhere from millions to a few billion stars. That may sound enormous, yet beside a spiral giant, they are tiny. Many circle the Milky Way and Andromeda in long, looping orbits, held by gravity but often distorted by it as well. Some are rich in ancient stars. Others seem almost ghostly, dim and sparse, as if they are already being pulled apart. What makes them so important is not just their size, but what they reveal. These little galaxies may preserve clues about the early universe, because many formed long ago and changed little compared with their larger neighbors. They are also thought to be rich in dark matter, making them useful laboratories for one of astronomy's deepest mysteries. So these small companions are not background decoration. They are some of the most revealing objects in our galactic neighborhood. Some galaxies leave long rivers of stars behind them. When gravity begins to tear a galaxy apart, the damage does not happen all at once. It unfolds slowly, beautifully, and with astonishing scale. As a smaller galaxy swings around a larger one, tidal forces can stretch its stars into immense streams that trail across space like rivers of light. These streams may arc around the host galaxy for tens or even hundreds of thousands of light years, preserving the path of an ancient encounter. To astronomers, they are not just lovely features. They are evidence. They show where a galaxy has been, how it has been distorted, and what invisible mass may surround the larger system pulling on it. In our own Milky Way, several such stellar streams have already been found, remnants of past encounters that are still unfolding overhead. They reveal that galaxies do not simply grow by forming new stars. They also grow by unraveling others, leaving behind long, luminous traces that tell the story of cosmic capture. Colliding galaxies can fling stars into intergalactic exile. A galactic collision is not usually a crash of star against star. The distances inside galaxies are too vast for that. Instead, it is gravity that does the violence. During close encounters and mergers, gravitational forces can yank stars from their familiar orbits and hurl them far beyond the main body of either galaxy. Some are cast into long tidal tails. Others are thrown so far out that they may never return, becoming wanderers of the space between galaxies. This is one way intergalactic space comes to hold stars with no clear home. Imagine a star that formed in the thick brightness of a galaxy, only to be flung into comparative solitude by a collision unfolding over millions of years. It would still shine, still age, and perhaps still carry planets, but now in a much lonelier setting. These exiles are reminders that galaxies are not sealed systems. Their stars can be uprooted and sent adrift by the slow brutality of gravity. Entire galaxies can be stripped like fruit under gravitational pressure. A small galaxy passing too close to a much larger one can suffer a fate that is both elegant and brutal. Gravity does not merely tug on it as a whole. It pulls harder on the near side than the far side, stretching the smaller system until its gas, stars, and dark matter begin to peel away. Over time, the galaxy can lose its outer layers, then its inner structure, until very little remains except a denser core or a faint stream of debris. This process is called tidal stripping, and it is one of the main ways larger galaxies grow by taking from smaller ones. The image of a fruit being peeled is surprisingly fitting. Layer by layer, a galaxy can be dismantled by forces it cannot resist. What remains may orbit for a while as a damaged remnant, or vanish into the halo of its conqueror. In this way, intergalactic space becomes the scene of slow destruction, where even whole galaxies can be carefully unmade. Intergalactic space holds stars that belong to no galaxy at all. It may seem natural to assume every star must belong to a galaxy, just as every house belongs to a town. But the universe is stranger than that. Astronomers have found stars drifting in the space between galaxies, unattached to any obvious stellar city. These are called intergalactic stars, and they likely began life inside galaxies before being pulled free during mergers, close passes, or the gradual shredding of smaller systems. In crowded galaxy clusters, there may be vast populations of them, scattered through the common space like sparks blown from a fire. They are hard to detect because they are so spread out, but their collective glow can sometimes be measured as a faint light between galaxies. That faintness makes the idea even more haunting. There are stars out there shining in relative solitude, far from the dense neighborhoods where stars are usually born. The universe contains not only cities of stars, but also lonely lights wandering between them. Some of those wandering stars may carry planets with them. If a star is torn from its galaxy, what happens to the planets that circle it? In some cases, they may go along for the ride. Planets orbiting close enough to remain gravitationally bound could continue circling their star even after both have been flung into intergalactic space. That means there may be complete planetary systems traveling through the darkness between galaxies, carrying suns, worlds, and perhaps moons into a setting with no familiar galactic skyline around them. The night on such a world would be unlike anything we know. Nearby stars would be scarce. The parent star would dominate the sky, while the rest of the universe would appear as distant smudges and isolated points. The idea feels almost fictional, yet it follows naturally from what gravity can do during galactic encounters. When stars are exiled, their worlds do not always get left behind. Entire systems may be carried outward, turning intergalactic space into a place that holds not only stars, but homes. A planet could drift through intergalactic darkness with no sunrise ever. Some worlds may never know the daily return of morning. A planet that has lost its parent star, or formed without one, could wander through deep space as a rogue world. Between galaxies, such a place would be surrounded by a darkness almost impossible to imagine. There would be no bright nearby sun climbing over a horizon, no blue sky, no daylight warming the ground. The main light might come only from distant stars and the dim combined glow of faraway galaxies. At first, that sounds like a frozen death sentence, and often it would be. Yet if the world were large enough, or retained internal heat from its formation and radioactive elements, it might still keep subsurface warmth for ages. Beneath ice, hidden oceans could remain liquid. So a planet without sunrise is not only a scene of cosmic loneliness. It is also a reminder that in the universe, Even the darkest places may still hold surprising possibilities under the surface. Rogue worlds may roam the gulfs between galaxies unseen. Astronomers already suspect that planets wandering without stars are common inside galaxies. Extend that thought outward, and the possibilities become astonishing. Some of those rogue worlds may be flung completely beyond galactic boundaries during violent interactions, then continue traveling through intergalactic space in almost total invisibility. Such worlds would be desperately hard to find. A dark planet reflects little light and emits only a faint warmth if it has cooled for long enough. Unless it passes in front of a distant star or bends light through gravity in exactly the right way, it could remain unseen forever. This means the gulfs between galaxies may contain far more than we can easily detect. Not just gas and stray stars, but entire lost planets moving silently through the dark. It is a humbling thought. The visible universe may be only the bright surface of a far richer reality, with hidden worlds crossing vast distances unnoticed, never rising, never setting, and never announcing their existence. Galaxy clusters are wrapped in enormous halos of hot intergalactic gas. A galaxy cluster is not simply a pile of galaxies gathered in one place. Surrounding the member galaxies is an immense atmosphere of hot gas that fills the space between them and extends across the cluster as a whole. This gas forms a huge halo, held in place by the combined gravity of the cluster, including the pull of dark matter. It is heated to such extreme temperatures that it shines in X-rays rather than visible light, which is why ordinary eyes cannot see it. Yet in terms of scale, it can be one of the dominant visible features of the cluster. Imagine hundreds or even thousands of galaxies embedded inside a shared ocean of blazing plasma. That is closer to the truth than the usual image of separate islands in empty darkness. The cluster has a common envelope, a vast medium that surrounds its galaxies, shapes their behavior, and reveals that the space between them is not a gap, but a major part of the system itself. That gas can outweigh all the stars in the cluster. When people picture a galaxy cluster, they usually imagine the stars doing most of the visible work. After all, stars are the bright part. They are what catch the eye and define the beauty of galaxies. Yet the real balance of ordinary matter in a cluster is far more surprising. The hot gas filling the space between the galaxies can outweigh all the stars in those galaxies combined. That means the most familiar objects in the cluster are not actually its main visible ingredient. The great bulk of its normal matter is spread through the intergalactic medium, thin and hot and almost invisible except in X-ray observations. This changes how you think about cosmic structure. A cluster is not mainly a gathering of glittering galaxies. It is a massive system where galaxies are embedded in something even larger and heavier than their combined starlight suggests. The bright pieces may seem central to us, but much of the cluster's true substance lies in the glowing gas between them. Intergalactic plasma glows brightest in powerful X-rays. The hottest gas in the universe does not announce itself with visible color. It reveals itself in radiation far beyond human sight. When intergalactic gas reaches temperatures of millions of degrees, it becomes plasma and emits strongly in X-rays. That is why X-ray telescopes have transformed our view of galaxy clusters and the wider space around them. Through them, astronomers can see blazing structures where ordinary telescopes show almost nothing at all. A cluster that looks like scattered galaxies in visible light can become, in X-rays, a giant glowing cloud with texture, turbulence, and scars from past collisions. This is one of the most dramatic reminders that the universe has layers hidden from our senses. A place that seems dark may actually be radiant in another band of light. The cosmos is not only what our eyes can catch. Some of its grandest structures shine in fierce, invisible colors, and only by building new eyes have we learned how luminous the intergalactic realm can be. astronomers find intergalactic matter by studying what it blocks. Some of the most important discoveries in astronomy come not from what shines, but from what gets in the way. Much of the material between galaxies is too faint to see directly, so astronomers search for it by looking at bright objects far beyond it. When light from a distant source passes through thin gas, specific wavelengths are absorbed, leaving tiny missing pieces in the spectrum. Those absences act like signatures, showing what kinds of atoms were present and how fast they were moving. In other words, the invisible becomes known by the bite it takes out of light. This is an elegant way of reading the universe. Instead of waiting for dim matter to glow, astronomers let bright background beacons do the work. The result is a map built from interruptions, shadows, and subtle losses. It is almost poetic. The hidden substance between galaxies can reveal itself by standing briefly in the path, turning missing light into one of astronomy's most powerful tools. Quasars act like cosmic flashlights through intergalactic fog. To study faint material between galaxies, astronomers need background lights bright enough to shine through the darkness. Quasars are perfect for this. They are the blazing cores of active galaxies, powered by supermassive black holes feeding on surrounding matter, and they can outshine entire galaxies by themselves. Because they are so brilliant and so distant, their light travels through huge stretches of intergalactic space before reaching Earth. Along the way, gas clouds leave fingerprints on that light, allowing astronomers to examine matter that would otherwise be almost impossible to detect. This turns quasars into something like cosmic flashlights. They do not illuminate space in the ordinary sense, but their beams let us read what lies between us and them. A distant quasar can therefore reveal layers of otherwise hidden structure across billions of light years. One of the brightest objects in the universe becomes a probe for one of the faintest. It is an extraordinary pairing of brilliance and near invisibility. A single beam of quasar light can expose invisible space. Imagine a lighthouse beam crossing a dark ocean and revealing fog, spray, and currents that would otherwise remain unseen. Quasar light works in a similar way, except on a scale so large it strains belief. A single line of sight from Earth to one distant quasar can pass through many separate clouds and filaments of gas. Each one leaves its own absorption marks in the quasar's spectrum, creating a layered record of the matter along that path. By decoding those marks, astronomers can learn the composition, motion, and distribution of material spread across immense reaches of intergalactic space. It is astonishing that one narrow beam can carry so much information. Even though we are only sampling a tiny line through the universe, that line can reveal hidden structure at many distances and epochs. So a single quasar is more than a faraway light. It becomes a vertical slice through cosmic history, exposing invisible space one delicate spectral mark at a time. Hydrogen between galaxies leaves delicate fingerprints in passing light. Hydrogen is the most common element in the universe, and in the space between galaxies it plays the role of a quiet witness. When light from something distant passes through thin clouds of hydrogen gas, the atoms absorb very specific wavelengths. In the spectrum, that produces narrow lines, subtle marks that show where the gas was and how far away it lies. Because light from remote quasars may pass through many such clouds, the spectrum can become filled with a forest of lines, each one tracing a separate patch of intergalactic hydrogen. This is one of astronomy's most beautiful techniques. A nearly invisible substance writes its presence into light with extraordinary precision. From those marks, astronomers can reconstruct the distribution of gas across enormous volumes of the universe. It is a kind of cosmic handwriting, faint and exact. The space between galaxies may look black to us, but hydrogen keeps signing its name across every suitable beam of light that crosses the dark. Those fingerprints map ancient structure across billions of light years. Once astronomers realized that absorption lines from hydrogen could be read like markers along a path, those lines became a way to map the large-scale universe. Each set of marks corresponds to gas at a different distance, which means a single spectrum records structure across vast spans of space and time. By collecting many such observations from many directions, astronomers can reconstruct where intergalactic gas gathered, how it clustered, and how that pattern changed as the universe aged. The result is not a simple picture of scattered clouds. It is a history of structure itself, stretching across billions of light years. These delicate marks reveal where matter was beginning to gather into the filaments and nodes that would later shape galaxies and clusters. In that sense, they let us watch architecture emerging from the early cosmos. Tiny missing slivers in light become a map of growth on the largest scales, showing how the universe built its immense framework over time. Intergalactic gas can reveal where missing ordinary matter was hiding. For decades, astronomers faced an awkward problem. Calculations of the early universe showed how much ordinary matter should exist, yet later counts of stars, galaxies, and gas came up short. A large share of normal matter seemed to be missing. It was not dark matter. It was the familiar kind, built from protons and neutrons, but too hard to find. The leading answer turned out to lie in diffuse gas between galaxies, especially in a warm to hot state that is difficult to detect directly. By studying absorption lines in the light from distant objects, astronomers began locating that elusive material in the web of intergalactic space. So the missing matter was not really lost. It was hidden in plain sight, spread too thinly and heated in ways that made it easy to overlook. That discovery is deeply satisfying. It shows that some of the universe's biggest mysteries are solved not by exotic ingredients, but by finding the ordinary where nobody expected it. The cosmic web was predicted long before we could truly trace it. One of the most satisfying moments in science is when theory sketches something years before technology can properly reveal it. The cosmic web is a beautiful example. Long before astronomers could map it clearly, simulations of the evolving universe suggested that matter should gather into a network of filaments, nodes, and voids under the pull of gravity. Starting from tiny density variations in the early cosmos, the models showed structure growing into a vast connected web rather than a random spray of galaxies. At the time, this was a bold picture of a universe few could directly observe. Later, with larger surveys and better techniques, the real distribution of galaxies and gas began to match that vision remarkably well. It was as though mathematics had glimpsed the shape of the universe in advance. That gives the web a special kind of wonder. It is not only grand in scale. It is also a triumph of human imagination, reason, and patient observation working together. Giant filaments connect galaxy clusters across astonishing distances. On the largest maps of the cosmos, galaxy clusters do not sit alone like scattered lights on velvet. They are linked by filaments, immense strands of matter stretching across tens and sometimes hundreds of millions of light years. Along these colossal bridges, galaxies are not arranged at random. They gather in long chains, following the deep channels carved by gravity over cosmic time. A single filament can guide matter from sparse regions into the dense knots where great clusters grow. If you could rise high enough above the universe to see the pattern whole, it would not look like chaos. It would look like structure on a breathtaking scale, a network so vast that even clusters become only bright intersections along it. These filaments are among the largest known features in existence. They turn intergalactic space into a connected landscape, where the greatest cities of stars are joined by roads built not of stone, but of matter itself. Between those filaments lie voids so empty they seem unreal. For every great strand in the cosmic web, there is a vast hollow beside it. These voids are not simply regions with fewer galaxies. They are enormous cavities where matter is astonishingly scarce, so sparse that they can feel almost impossible to accept as real. Some span hundreds of millions of light years, yet contain only a thin sprinkling of galaxies and gas. If you lived inside one, the sky might hold far fewer neighboring galaxies than astronomers see from Earth. The universe would look lonelier, darker, and strangely unfinished. What makes these regions so captivating is their scale. We are used to associating greatness with abundance, but voids show the opposite. The absence itself becomes the wonder. They are part of the universe's design, not mistakes or leftovers. The cosmic web needs emptiness as much as density. Without these giant hollows, the filaments and clusters would not stand out as the magnificent structure they do. Some voids contain only a few lonely galaxies. Even the emptiest regions are rarely perfect deserts. Here and there, inside vast cosmic voids, a few galaxies remain, scattered and isolated like remote villages in a huge wilderness. These lonely systems live far from the crowded environments where galaxies more often gather, merge, and compete. That isolation makes them scientifically precious. Their histories can be quieter, less shaped by repeated encounters, which means they may preserve clues about how galaxies behave when almost entirely left alone. Imagine a galaxy growing in near solitude, with no great neighboring cluster looming nearby and no busy stream of companions crossing its path. Its stars may still form, its gas may still swirl, and its dark matter halo may still hold it together, but its cosmic life unfolds in a much calmer setting. In a universe famous for its crowds and collisions, these rare residents of the void feel almost intimate. They are reminders that even emptiness can still shelter islands of light. Galaxies near voids can spin and evolve differently. Location matters in the universe, and not just in the obvious sense. A galaxy's environment can shape how it grows, what gas it gathers, how often it collides, and even how it spins. Near the edges of voids, some galaxies appear to behave differently from those deep inside crowded clusters. Their angular momentum may align with nearby filaments, and their histories may be less disturbed by frequent interactions. That means the quiet geometry of the cosmic web can influence something as intimate as the turning of a galaxy's disk. The thought is astonishing. The largest structures in the universe may help shape the internal motion of individual galaxies. A galaxy is not only a self-contained system, it is part of a broader landscape that can guide its fate over billions of years. So the cosmic web does more than hold galaxies in place. It helps choreograph them, giving spin and direction to star cities growing at the boundaries of immense cosmic emptiness. The largest structures in existence are written across intergalactic space. When people imagine the grandest things in the universe, they often picture giant stars, black holes, or enormous galaxies. Yet the truly largest known structures are bigger than any single galaxy by a staggering margin. They are written across intergalactic space itself, in the form of filaments, walls, superclusters, and vast connected patterns of matter that span hundreds of millions of light years. These are not compact objects with neat edges. They are immense arrangements, subtle and sprawling, revealed only when astronomers map huge swaths of the cosmos at once. Their existence changes your sense of scale. A galaxy that seems unimaginably vast up close becomes only one luminous node in something far greater. Entire clusters shrink into points within larger patterns. Intergalactic space is where these structures live, and where their full shapes become clear. If you want to find the universe at its grandest, you do not look only at the bright objects. You look at the enormous design between them. Matter in the universe gathers like dew along invisible threads. Gravity does not pull matter into the universe in neat straight lines or tidy circles. It gathers matter into patterns that can feel organic, almost like moisture collecting along the finest strands of a spider's web at dawn. Gas and galaxies accumulate along filaments shaped by deeper hidden structure, concentrating where gravity is strongest and thinning where it is not. The comparison to dew is useful because it captures both delicacy and inevitability. Matter is not thrown about randomly. It settles, pools, and gathers along preferred paths that are not always visible at first glance. In the cosmos, those hidden guides are tied to the distribution of dark matter and the earliest density variations after the universe began. The result is a web where the bright visible parts are only the gathered surface of a deeper arrangement. It is a beautiful image to keep in mind. The universe does not merely contain matter. It lets matter collect along unseen lines until vast structure appears. Dark matter helps sculpt the roads galaxies travel between. Much of the universe's structure owes its shape to something we still cannot see directly. Dark matter does not shine, reflect, or absorb light in the ordinary way, yet its gravity helps build the framework on which galaxies later form and move. Long before visible galaxies fully emerged, dark matter gathered into halos and filaments, creating a network of gravitational channels. Ordinary matter then fell into those channels, cooling and condensing into gas clouds, stars, and galaxies. In that sense, dark matter helped lay the roads before the luminous travelers arrived. The galaxies we see today are following a map, first drawn by an invisible substance. That idea is one of the most astonishing in modern science. The visible universe may be a brilliant tracing of something fundamentally hidden. Intergalactic space, with all its filaments and nodes, is shaped not just by what we can observe, but by a deeper scaffold whose presence is known mainly through the way gravity bends and builds everything around it. Ordinary gas follows those dark scaffolds through deep space. Once dark matter gathers into halos and filaments, ordinary matter responds. Gas begins to fall into the gravitational valleys set by that unseen structure, tracing the same broad paths through the universe. Over time, this gas collects along filaments, feeds growing galaxies, and pools in the dense knots where clusters arise. In some places it remains diffuse and hot. In others it cools, thickens, and helps form stars. This means the visible gas of the universe is not wandering aimlessly. It is flowing along a hidden architecture. The image is striking. An invisible scaffold reaches across deep space, and familiar matter pours into it, like rainwater following the shape of a buried landscape. Galaxies then emerge where conditions are richest. So when astronomers map gas between galaxies, they are often tracing the visible edge of something more fundamental underneath. The luminous universe is not built from scratch. It is following lines already laid down by a darker and far older structure. Intergalactic space helped turn tiny early ripples into galaxies. The early universe was astonishingly smooth, but not perfectly so. Tiny ripples in density, almost unimaginably slight, were present in the young cosmos. Those minute differences mattered enormously. Over billions of years, gravity amplified them. Regions that were a little denser attracted more matter, growing into the first filaments, halos, and eventually galaxies. Intergalactic space was not a passive background during this transformation. It was the arena where those ripples expanded into structure. Gas moved, gathered, and heated there. Matter fell along invisible gradients there. The first great patterns emerged there. Without those broad intergalactic regions, the universe could never have grown from faint fluctuations into the rich architecture we see today. It is extraordinary to think that galaxies began as slight unevenness in a nearly uniform cosmos. The star cities we admire and the planets and people within them all trace back to tiny primordial differences that deep space slowly stretched into something grand, luminous, and enduring. The universe's grandest architecture lives where almost nothing seems to be. There is a wonderful contradiction at the heart of cosmology. The regions that seem emptiest are often the ones that reveal the universe's biggest design. Intergalactic space can look like blackness punctuated by a few distant lights, yet when astronomers map it carefully, it becomes the place where the full architecture of the cosmos appears. Filaments, voids, halos, and superclusters are not written inside one galaxy. They are written across the spaces between galaxies. That means the universe saves some of its greatest revelations for places that first seem empty. The lesson is almost philosophical. What looks like absence can contain pattern on the largest imaginable scale. It is only when we stop focusing on individual bright objects that the deeper shape emerges. In ordinary life, we often notice the nearest and loudest things first. The cosmos asks for a different kind of attention. Its grandest structure is revealed in the dark, sparse regions where almost nothing appears to be happening. Early intergalactic hydrogen once filled the cosmos like a fog. There was a time when the universe had stars nowhere and hydrogen almost everywhere. After the earliest searing phase of cosmic history, matter cooled enough for atoms to form, and neutral hydrogen spread through space in immense abundance. It filled the young cosmos like a fog, not thick in the everyday sense, but widespread enough to absorb energetic light and dim much of what lay beyond it. This was before galaxies had fully transformed the darkness. The universe had structure beginning to grow, but it was still wrapped in a great haze of unlit hydrogen stretching across intergalactic space. That fog shaped everything that came next, because it controlled how radiation traveled and how the first luminous sources affected their surroundings. When we imagine the early universe, it is tempting to picture immediate brilliance. In reality, there was a long interval where darkness and hydrogen ruled together. The cosmos had matter, direction, and potential, but much of its great visible story had not yet begun. The first stars transformed that fog with fierce ultraviolet light. The arrival of the first stars changed the universe in a profound and violent way. These early stars were likely massive, hot, and brilliant beyond comparison with many stars we know nearby today. Their ultraviolet radiation poured into the surrounding hydrogen fog and began tearing electrons from atoms, turning neutral gas back into ionized plasma. This process did not happen everywhere at once. Bubbles of transformed space spread outward from the first luminous sources, growing, overlapping, and slowly eating away the ancient fog. It was as though the young universe was being switched on in patches. Darkness did not simply fade. It was actively burned back by light. That makes the first stars more than bright objects. They were agents of cosmic change, reshaping the state of intergalactic space itself. Their existence altered how radiation moved, how gas behaved, and how future galaxies evolved. In a very real sense, the first stars were among the universe's great revolutionaries. Intergalactic space remembers when the universe first became transparent. There was a turning point in cosmic history when the universe changed from being opaque to being transparent. Before that, light could not travel freely for long without being scattered. Afterward, radiation could move across great distances, allowing the cosmos to reveal itself in a completely new way. Intergalactic space still carries the memory of that transition. The state of its gas, the background radiation that fills it, and the signals astronomers detect from great distances all preserve clues about when the young universe opened itself to light. This is one of the reasons deep space is so scientifically powerful. It acts like an archive of phase changes on a cosmic scale. The transparency of the universe was not a trivial detail. It made observation, structure, and later, illumination possible. Everything we can see across great distances depends on that ancient shift. So the darkness between galaxies is not forgetful. It still holds evidence of the moment the universe first became see-through. Ancient radiation still crosses intergalactic space from the early universe. All around us, even now, there is a faint sea of radiation left over from the young universe. It is not coming from stars or galaxies. It is older than both in their familiar forms. This ancient light, stretched by cosmic expansion into microwaves, moves through intergalactic space in every direction. It is the afterglow of a much earlier epoch, preserved across billions of years. What makes it so remarkable is not only its age, but its persistence. The universe has changed enormously since that radiation first began its journey, yet it still fills the cosmos like a whisper that never fully faded. Sensitive instruments can detect it and read tiny variations in its temperature, using those fluctuations to learn about the earliest seeds of structure. This means intergalactic space is not silent. It is still carrying a message from almost the beginning, a message that has survived the rise of galaxies, stars, planets, and life itself. Every distant galaxy is seen through layers of intergalactic history. When we look at a remote galaxy, we are never seeing it in isolation. Its light has crossed immense stretches of space on the way to us, and along that journey, it has passed through gas, radiation fields, and structures that belong to different eras of cosmic history. Each stretch adds something to the story. Some absorb certain wavelengths. Some reveal the expansion of the universe. Some preserve information about the chemical state of intergalactic gas at earlier times. So every distant galaxy arrives wrapped in context. The light does not simply show us the source. It also shows us what stood between that source and Earth across billions of years. This makes every deep observation richer than it first appears. A distant galaxy is not just a remote island of stars. It is a beacon whose light has sampled the universe on its way here. To study that light is to study a layered record of the cosmos itself. Looking farther away means looking through younger cosmic ages. Distance in astronomy is also time. Because light takes time to travel, seeing something very far away means seeing it as it was long ago. A galaxy 1,000,000 light years away appears 1,000,000 years in the past. Push that distance farther, and the effect becomes extraordinary. The deepest images do not merely show remote places. They reveal younger chapters of the universe. Galaxies look smaller, stranger, and less settled, because we are seeing them before billions of years of evolution had time to unfold. This is one of the most thrilling aspects of studying intergalactic space. It turns the cosmos into a natural time machine. We do not have to imagine the early universe only through theory. We can actually observe it in stages, provided we look far enough. That gives deep astronomy a special drama. Each greater distance is also an earlier scene. The farther the light has traveled, the younger the cosmic story we are witnessing. Intergalactic space lets astronomers study time as much as distance. Because light takes ages to cross the universe, the space between galaxies becomes more than a gap. It becomes a measure of time itself. Every additional stretch of distance corresponds to another interval of history, which means astronomers can use deep observations to compare different epochs of cosmic evolution. Nearby galaxies show later chapters. Distant ones reveal earlier chapters. gas clouds at different redshifts trace changing conditions in intergalactic space across billions of years. In this way, the universe is arranged almost like a layered record, with time spread out through distance. That is one reason cosmology feels so unusual compared with other sciences. Researchers are not only studying faraway places, they are studying the past directly, using light that began its journey when the cosmos was younger. Intergalactic space makes this possible by preserving those enormous travel times. It turns observation into chronology. The darkness between galaxies becomes the very medium through which the history of the universe can still be read. Some of the earliest galaxies lit up the darkness between galaxies. Before there were grand spirals and giant ellipticals, there were much younger systems beginning to shine in a darker cosmos. These early galaxies were small compared with many modern ones, yet their impact was enormous. Packed with hot young stars, they poured radiation into surrounding space and helped transform the intergalactic medium. Their light did not remain trapped within their own boundaries. It leaked outward, brightening nearby darkness and contributing to the long process that reionized the universe. In that sense, the first galaxies were not only forming themselves, they were also reshaping their surroundings. They acted like lanterns in a foggy landscape, carving out growing regions of clearer space around them. When astronomers search for these primitive systems, they are looking for some of the first builders of a transparent universe. Their importance lies not just in their existence, but in their effect. The early galaxies helped make the wider cosmos more visible for everything that followed. The first black holes may have changed intergalactic space itself. Black holes are often imagined as local monsters, devouring nearby matter and warping their immediate surroundings. But the earliest black holes may have influenced much more than their own neighborhoods. If some formed quickly and began feeding efficiently, they could have released intense radiation into the young universe, heating and ionizing gas beyond their host systems. In effect, they may have helped alter the state of intergalactic space itself. This possibility is thrilling because it gives black holes a role not only in galactic centers, but in broad cosmic transformation. The first ones may have been among the universe's earliest engines, contributing to the heating of surrounding gas and changing how matter cooled and gathered afterward. Their fingerprints may still linger in the timing and texture of early cosmic evolution. So the first black holes were not merely dark endpoints of stellar collapse. They may have been major players in shaping the wider environment between the first generations of galaxies. Even emptiness has a history written by starlight. It is easy to treat empty space as timeless, as though nothing happens there unless a bright object crosses it. Yet the darkness between galaxies has been changed again and again by radiation from stars, galaxies, and black holes. Light has heated it, ionized it, passed through it, and left subtle clues about each stage of cosmic evolution. In that sense, deep space has a biography. Its gas has shifted state. Its chemistry has changed. Its transparency has evolved. The early universe, the first stars, the rise of galaxies, and the activity of black holes have all written something into intergalactic space. Starlight is one of the main authors of that story. It does not merely illuminate, it transforms. This is why the great apparent emptiness of the cosmos is so misleading. It is not a blank backdrop. It is a place that has been acted upon for billions of years. Even where almost nothing seems to be present, history is still written there in light. Supermassive black holes can blast matter far into intergalactic space. At the heart of many large galaxies sits a black hole, with a mass millions or even billions of times greater than the Sun. When gas falls toward one of these giants, not all of it disappears. Some of it is heated to extraordinary temperatures in a swirling disk, then flung outward with tremendous force. These outflows can blast matter far beyond the galaxy itself, pushing gas into the surrounding intergalactic medium. In some cases, the expelled material travels so far that it helps pollute space between galaxies with heavier elements forged in stars. That means carbon, oxygen, and iron can be thrown out of galaxies by the activity of a black hole, enriching regions that once held only simpler ingredients. It is a staggering image. A dark object known for swallowing matter can also help launch it outward across cosmic distances. The centers of galaxies are not only graveyards. They can be engines, hurling material into the wider universe with astonishing power. Galactic jets can punch through space for hundreds of thousands of light years. Some black holes do more than drive broad winds. They fire narrow jets, focused beams of particles and energy that shoot from the regions near the black hole at nearly the speed of light. These jets can remain coherent over astonishing distances, stretching far beyond the visible body of the host galaxy. In some radio galaxies, they extend for hundreds of thousands of light years, and in the most extreme cases, even farther. That is difficult to picture. A process unfolding near a region smaller than the solar system can launch streams that reach across scales larger than entire galaxies. Along their paths, these jets carve through surrounding gas, inflate lobes, and leave glowing traces visible in radio waves. They are among the most dramatic examples of small origins creating enormous consequences. A compact central engine buried in a galactic core can project influence across intergalactic space on a scale that turns a whole galaxy into only the starting point. Those jets heat gas far beyond the galaxies that launched them. When a powerful jet plows into the gas around a galaxy, it does not simply pass through without consequence. It transfers energy into the surrounding medium, driving shocks, stirring turbulence, and inflating giant cavities in the hot gas that fills groups and clusters. The result is heating on a scale far beyond the galaxy that launched the jet. In some clusters, astronomers can actually see huge bubbles in the X-ray glow of the gas, as though invisible hands have punched holes into a blazing cosmic atmosphere. Those cavities mark where black hole activity has deposited energy into the intergalactic medium. This is one of the strangest forms of influence in the universe. A black hole hidden in a galactic center can keep distant gas hot across a region vastly larger than the galaxy itself. The effect is not local. It is environmental. The black hole becomes part of the climate system of intergalactic space, shaping the thermal state of an entire cosmic neighborhood. Radio galaxies can light up intergalactic space like cosmic beacons. Some galaxies are almost modest in visible light, yet in radio waves they become vast and magnificent. These are radio galaxies, systems whose central black holes power enormous jets and lobes that shine strongly at long wavelengths. The radial-emitting structures can extend far outside the host galaxy, filling intergalactic space with giant glowing forms that ordinary eyes could never see. If human vision were sensitive to radio light, some of these galaxies would look less like compact islands and more like colossal beacons with wings or plumes stretching across hundreds of thousands of light years. What makes them especially captivating is their scale and contrast. A relatively small galactic core can produce structures so huge that the visible galaxy seems like only the bright center of a much larger invisible phenomenon. These radio lobes reveal where energy is being deposited into space between galaxies. They turn the dark around a galaxy into part of the spectacle, showing that a galaxy's true reach may extend far beyond its stars. Black hole outbursts can prevent cluster gas from cooling too quickly. In a galaxy cluster, the hot gas between galaxies should, in theory, radiate energy away and cool over time. If that cooling happened unchecked, huge amounts of gas might condense and form stars at rates much greater than astronomers actually observe. Something is stopping that from happening, and one of the main suspects is black hole feedback. Outbursts from supermassive black holes, especially in the largest central galaxies of clusters, inject energy back into the surrounding gas through jets, shocks, and inflated bubbles. That reheating can slow or prevent rapid cooling. It is an elegant piece of cosmic regulation. A black hole, often imagined only as a destroyer, may help control the life cycle of gas in an entire cluster. Without that feedback, clusters could evolve very differently. The hottest regions might lose energy too fast, and star formation could run wild in places where it does not today. Even on the largest scales, the universe seems to balance itself through dramatic mechanisms. Intergalactic gas can ripple when galaxy clusters collide. A collision between galaxy clusters is not an ordinary crash. It is a slow, immense convergence of structures containing hundreds or thousands of galaxies, vast halos of dark matter, and huge reservoirs of hot gas. When two clusters merge, their intergalactic gas does not remain calm. It can be stirred into ripples, waves, and sloshing motions that spread through the cluster medium for hundreds of millions of years. Astronomers have observed signs of these disturbances in X-ray images, where sharp edges and curved patterns reveal that the hot gas has been displaced and set into motion. The effect is almost like watching a giant bowl of liquid shudder after being struck, except the bowl is millions of light years across, and the liquid is plasma heated to millions of degrees. These ripples matter because they transport energy, mix material, and preserve evidence of past encounters. The space between galaxies can remember impact not only through scars, but through motion that continues long after the initial collision. Some collisions create shockwaves larger than entire galaxies. When clusters of galaxies merge, the violence unfolds mostly in the gas between them. As great clouds of hot plasma slam together, they can generate shockwaves that travel across intergalactic space on scales so huge they dwarf individual galaxies. These are not subtle disturbances. They are enormous fronts where temperature, density, and pressure change abruptly, moving through the cluster medium like cosmic sonic booms. In some observed systems, the shock structures stretch for millions of light years. That means a single wave can be larger than the Milky Way many times over. The scale alone is breathtaking. We're used to thinking of galaxies as the giants of space. Yet in cluster collisions they become small players inside even larger violence. These shock waves heat gas, accelerate particles, and leave long-lasting signatures that telescopes can detect in X-rays and radio waves. Intergalactic space is not just a backdrop for collisions. It is where the biggest part of the blast actually happens. Cluster mergers are among the most violent events since the Big Bang. There are few events in the modern universe that can rival the raw energy involved when galaxy clusters merge. Each cluster contains not only galaxies, but also immense gas reservoirs and vast masses of dark matter. When two such systems fall together under gravity, the energy released is extraordinary, second only to the Big Bang itself in some comparisons of large-scale cosmic events. Yet this violence unfolds in eerie silence and over immense spans of time. Galaxies mostly pass without direct stellar collisions, while the hot gas between them crashes, compresses, and heats. Dark matter components can pass through more cleanly, revealing striking separations between visible matter and invisible mass. These mergers help astronomers test the nature of dark matter and understand how the biggest bound structures in the universe grow. They are not side notes in cosmic history. They are defining episodes. Whole clusters, each already immense, combine to form something larger, and in doing so, release energy on a nearly unimaginable scale. Intergalactic magnetic fields stretch across places almost utterly empty. Magnetic fields are familiar on Earth. They guide compasses, shape auroras, and thread through stars and planets. What is far less intuitive is that magnetic fields also seem to extend across intergalactic space, where matter is so sparse that the environment feels almost empty. Yet observations suggest that even these thin regions can host magnetic fields stretched across huge distances. They are weak compared with a refrigerator magnet, but over cosmic scales they matter. They can influence the motion of charged particles, shape radio-emitting structures, and preserve clues about processes from the young universe or later galactic activity. The truly astonishing part is not merely that they exist, but that they persist in such tenuous places. Space between galaxies is not only threaded by matter and gravity. It may also be laced with invisible magnetism. That gives the cosmos another hidden layer of structure. Even where there is almost nothing to touch, there may still be an invisible field extending across the dark. No one knows exactly how those vast magnetic fields began. Astronomers know intergalactic magnetic fields are there, or at least have strong evidence that they are, but their ultimate origin remains uncertain. That mystery makes them especially compelling. Perhaps tiny seed fields were created in the young universe itself, during early cosmic transitions or inflation. Perhaps later galaxies and black holes generated magnetized outflows that gradually spread into intergalactic space. Perhaps both contributed, layering cosmic history into the magnetic environment we observe today. Each possibility carries a different story about how the universe built its invisible structure. The puzzle matters because magnetism can affect how particles move, how gas behaves, and how energy spreads through the cosmic web. Yet unlike stars or galaxies, magnetic fields cannot simply be photographed in the ordinary sense. Their presence must be inferred through subtle effects on light and matter. So one of the universe's broadest features remains partly hidden from explanation. Even now, we can trace these great magnetic threads without fully knowing where the first strand began. Tiny particles race through intergalactic space at almost light speed. Not everything traveling through intergalactic space is slow and majestic. Some of it is astonishingly fast. High-energy particles, including protons and atomic nuclei, can be accelerated to speeds so close to light that the difference is almost meaningless in everyday terms. These particles may be launched by supernova remnants, active galactic nuclei, or violent shocks in clusters, and set loose into the wider universe. Once traveling, they can cross enormous distances, guided and deflected by magnetic fields along the way. Their journeys are difficult to reconstruct because those fields scramble their paths, but their presence reminds us that deep space is not static. It is alive with movement at nearly the ultimate speed limit of nature. A region that looks empty and still may in fact be crossed by particles carrying enormous energy from distant cataclysms. Intergalactic space is not only the realm of slow gravitational architecture, it is also a racetrack for some of the fastest travelers in the cosmos. Cosmic rays may spend ages wandering between galaxies. A high-energy particle released into space does not always travel in a straight heroic line from source to destination. In many cases it wanders. Magnetic fields, even weak and diffuse ones, can bend the paths of charged particles again and again, turning a direct route into a tangled journey. That means some cosmic rays may spend immense spans of time wandering through intergalactic space before ever reaching a galaxy, a cluster, or a detector on Earth. Their paths can become so twisted that by the time they arrive, they no longer clearly point back to where they began. This makes them both frustrating and beautiful to study. They are messengers whose message has been smeared by the medium itself. Yet their existence also reveals something extraordinary. The universe is crossed by tiny projectiles carrying energies beyond the reach of most human machines, drifting and curving through the dark for ages. Intergalactic space can be a maze, and some particles may spend cosmic lifetimes inside it. Neutrinos can cross intergalactic space almost as if nothing exists. If cosmic rays are the wanderers of deep space, neutrinos are the ghosts. These tiny particles interact so weakly with matter that they can pass through stars, planets, and immense stretches of gas with almost no interruption. A neutrino born in a distant violent event, such as a supernova or an active galaxy, can cross intergalactic space with extraordinary indifference to everything in its way. That makes neutrinos precious messengers. They can carry information from environments where light may be trapped or distorted, reaching us from deep inside cosmic engines that are otherwise hard to probe. The downside is that they are famously difficult to catch. Vast detectors must wait patiently for the rare moment when one finally interacts. Still, the idea is thrilling. The universe may be filled with these near-invisible travelers streaming through the darkness in unimaginable numbers. Intergalactic space offers them almost no resistance. They move through the cosmos as though the great reaches between galaxies were hardly there at all. Gravitational waves travel through intergalactic space, carrying news of collisions. The universe does not communicate only with light and particles. It also sends news through ripples in space-time itself. Gravitational waves are produced when massive objects accelerate in extreme ways, especially when black holes or neutron stars spiral together and merge. Once created, these ripples spread outward across intergalactic space, carrying information about the collision that made them. What is remarkable is how directly they travel. They are not light, and they do not need matter as a medium. They move through the fabric of the universe itself, crossing the darkness between galaxies until they wash through Earth and ever so slightly stretch and squeeze space. Detecting them requires astonishing precision, but now that humanity has done it, the cosmos has gained a new language. Intergalactic space is not silent. It can carry vibrations from distant mergers across millions or billions of light years. A collision long ago and far away can still arrive here, not as an image, but as a passing shiver in space-time. Even light is subtly stretched while crossing expanding intergalactic space. When light leaves a distant galaxy, it begins a journey through a universe that is not standing still. Space itself is expanding, and while the light is in transit, that expansion stretches the wavelength of the light along with it. The result is known as cosmological redshift. Light that began bluer or more energetic can arrive redder and weaker, not because it wore out, but because the very fabric it crossed expanded beneath it. This is one of the most elegant ideas in cosmology. The journey changes the traveler because the route itself is changing. Intergalactic space is not a fixed stage between source and observer. It is an active participant in what the light becomes by the time it reaches us. That means every distant beam carries evidence not only of where it came from, but of the expanding universe it crossed. The darkness between galaxies does not merely separate objects. It stretches the messages that pass through it. The farther a galaxy is, the redder its light becomes. This is one of the great clues that revealed the expanding universe. Astronomers found that the light from distant galaxies is shifted toward the red end of the spectrum, and the farther away a galaxy is, the stronger that shift tends to be. The reason is not that galaxies are simply moving through static space like sparks in the wind. It is that space itself has expanded while their light was traveling. Greater distance usually means the light spent more time crossing expanding intergalactic space, so its wavelength was stretched more by the journey. This relationship between distance and redshift became a cornerstone of modern cosmology. It turned distant galaxies into markers of expansion, allowing astronomers to measure how the universe changes on its largest scales. There is something beautiful in the simplicity of it. The color of a galaxy's light can reveal the history of its voyage. A redder glow is not merely a hue. It is evidence of a larger cosmic motion. Expansion makes intergalactic distance grow while light is still traveling. Imagine sending a message across a landscape that keeps widening beneath it. That is essentially what happens in the expanding universe. A photon can begin its journey toward us, but while it is en route, the intergalactic space between source and observer continues to grow. This makes cosmic distance different from the ordinary distances we know on Earth. The gap is not fixed at the moment the journey begins. It changes during the journey itself. As a result, the final path light travels can be much greater than a simple first glance would suggest. This is one reason the universe becomes so difficult to picture with everyday intuition. In daily life, roads do not lengthen while you drive. In cosmology, the road really does expand beneath the traveler. Intergalactic space is dynamic, and light must contend with that dynamism every moment it moves. The universe is not only vast, it is actively changing the scale of the very distances it asks light to cross. Some galaxies recede so fast their future light may never reach us. Because the universe is expanding, there are galaxies so distant that the space between us and them is growing at an effective rate that outpaces the ability of newly emitted light ever to close the gap. This does not break relativity, because the galaxies are not racing through local space faster than light in the usual sense. Rather, the expansion of space itself is doing the work. The result is haunting. We may still receive light those galaxies emitted long ago, when conditions were different, but light they emit in the far future may never arrive. In a deep sense, parts of the universe are slipping beyond communicable reach. They are not vanishing instantly. They are becoming cut off by the growth of space. This gives the cosmos a kind of horizon, not a physical wall, but a limit to future visibility. Intergalactic space is not just separating galaxies. It is gradually deciding which parts of the universe can still send us news at all. Cosmic expansion turns intergalactic space into a moving frontier. Frontiers are usually thought of as boundaries waiting to be crossed, but in the universe, the frontier itself moves. As space expands, the distances between great structures grow, and the observable relationship between faraway regions changes with time. Galaxies drift farther apart, not because they are all driving through a fixed emptiness, but because the emptiness itself is stretching. This makes intergalactic space feel less like a static gap and more like a dynamic frontier, one that grows and reshapes the cosmic map as the ages pass. The farther outward we look, the more strongly we encounter this reality. Remote galaxies are not simply far away in the ordinary sense. They are embedded in a universe that has been widening throughout their light's journey. That moving frontier affects visibility, redshift, and the ultimate fate of cosmic structure. Intergalactic space is therefore not just where galaxies happen to be separated. It is one of the main ways the universe expresses its ongoing change. Distance in the universe is not as simple as empty miles. On Earth, distance feels straightforward. It is the length between one place and another. In cosmology, distance becomes far more slippery. There is the distance something had when it emitted its light, the distance its light actually traveled, and the distance it has now after billions of years of expansion. These are not always the same, which can make the universe feel almost mischievous to describe. A galaxy whose light has taken billions of years to reach us may now be vastly farther away than a plain light travel time would suggest. Intergalactic space is the reason. It expands, changes, and complicates any simple measuring tape we might want to imagine stretched across the cosmos. This is part of what makes astronomy so humbling. Even something as basic as how far away is it becomes layered and subtle on the grandest scales. In the universe, distance is not just separation. It is geometry, history, motion, and time, all at once. Our local group is falling toward a larger cosmic region. The Milky Way is not only orbiting within its own galaxy and drifting within the local group. The whole group is moving towards something larger. Our galactic neighborhood feels intimate on cosmic scales, yet it is being tugged by the gravity of surrounding structure, including massive concentrations of galaxies far beyond our immediate companions. Astronomers sometimes describe this as a kind of cosmic flow, where galaxy groups drift along the large-scale landscape shaped by matter on still greater scales. We are not sitting in a quiet pond. We are part of a current. That thought expands the sense of motion enormously. The Milky Way, Andromeda, their dwarf companions, and the dark matter that binds them are all participating in a larger journey through the universe. Even our local patch of intergalactic space is not fully local in its destiny. It belongs to a broader gravitational story, and we are already moving within it, whether we notice or not. The Virgo cluster helped shape our wider intergalactic neighborhood. Far beyond the local group lies the Virgo cluster, the nearest large cluster of galaxies to our own neighborhood, and one of the great masses shaping the region around us. It contains thousands of galaxies bound together in a vast shared halo of dark matter and hot gas. We are not members of that cluster, but its gravity still matters to us. Like a distant mountain influencing rivers far below, Virgo helps shape the motion of galaxies and groups across a wide region of space. It is one of the nearest examples of how structure scales upward in the universe. A small galactic family like ours sits inside a much broader environment, influenced by giants beyond it. To picture the Virgo cluster is to realize that our galaxy is not merely near a few local companions. It resides on the outskirts of a far grander landscape, where huge concentrations of matter help define the motions and futures of whole neighborhoods of galaxies. Entire galaxy groups drift within even greater superclusters. A galaxy group may sound impressive, and it is, but it is not the end of the nesting. Groups and clusters themselves are embedded within even larger arrangements called superclusters. These are not always tightly bound structures in the way a cluster is, but they mark immense regions where matter is more concentrated than average, and where the cosmic web becomes especially rich. Entire galaxy groups can drift within these broader domains, following the pull of the large-scale structure around them. The image is wonderful. A galaxy belongs to a group. A group belongs to a larger pattern. That pattern belongs to the web. Each level sits inside something vaster. This layered structure gives the universe a kind of grandeur that keeps unfolding no matter how far out you look. Intergalactic space is the medium that allows these nested scales to exist, holding not just isolated galaxies, but families of galaxies moving inside still greater realms that almost defy ordinary comprehension. Superclusters are linked across some of the largest known scales. Even superclusters do not stand alone. On the broadest maps, these giant concentrations of galaxies and groups are themselves connected by vast patterns, part of the same overarching web that stretches across the observable universe. The connections are not always dense or easy to define, but they reveal a cosmos whose largest scales still carry recognizable structure. This is one of the most arresting facts in astronomy. No matter how far out the view extends, the universe keeps showing organization. Great regions of matter lie along filaments and sheets, while immense voids open beside them. The result is that superclusters become less like isolated kingdoms and more like major provinces in a single cosmic geography. Intergalactic space is where this geography becomes visible. It is the parchment on which the grandest structures are drawn. The farther astronomers map, the more the universe resembles something deeply interconnected, with its largest known realms still linked by patterns spanning astonishing reaches of darkness. The Milky Way and Andromeda are both embedded in intergalactic gas. Between our galaxy and Andromeda lies more than open darkness. Both galaxies sit inside a broader environment that includes thin gas spread through the local group, a faint intergalactic medium shared by our galactic neighborhood. This gas is far too sparse to resemble anything familiar, yet on cosmic scales, it matters. It is part of the material reservoir from which galaxies may draw, part of the medium through which they move, and part of the wider setting in which their future interaction will unfold. In that sense, the Milky Way and Andromeda are not just two isolated islands facing each other across a pure void. They are immersed in the same broader sea. That gives their relationship a different feel. The darkness between them is not empty stage space. It is a shared environment, subtle and difficult to detect, but real. Our galaxy and its largest neighbor already inhabit a common intergalactic setting, long before their stars ever begin to mingle. Those two galaxies are already drawing closer through the dark. The Milky Way and Andromeda are not merely neighboring galaxies. They are on approach. Gravity has been drawing them together across intergalactic space for billions of years, and the motion continues now. Although the timescale is immense by human standards, the outcome is already written into their trajectory. The darkness between them is shrinking. That idea is astonishing when you remember what Andromeda is. It is not a small companion. It is a giant spiral galaxy containing hundreds of billions of stars, moving toward us across more than 2 million light-years. Yet the approach is so slow and the distance is so huge that the night sky still feels calm and permanent. Beneath that calm, a future encounter is developing. Intergalactic space between the two great galaxies is not static. It is being crossed by motion with a destiny. We live inside a galaxy already committed to a vast meeting, advancing through the dark toward another stellar continent. Their future collision will remake nearby intergalactic space completely. When the Milky Way and Andromeda finally begin their full interaction, the surrounding intergalactic environment will be transformed. The broad, relatively quiet region that separates them now will become a place of streams, shocks, disturbed gas, and stars flung into new trajectories. The two galaxies will not simply overlap like transparent images. Their gravitational fields will tear and reshape both systems, driving huge flows of material into the surrounding space. Gas clouds may collide and compress. Tidal features may spread far outward. New stars may form in regions that are now dark and sparse. Intergalactic space in our neighborhood will stop being the calm gulf it is today and become the active stage of a major cosmic reconstruction. This is one of the reasons the future merger is so captivating. It will not only remake the galaxies themselves, it will also reinvent the space around them, turning the local darkness into a temporary realm of upheaval, brilliance, and new structure. Stars will rarely strike, but galactic shapes will be torn apart. One of the strangest truths about galaxy collisions is that direct star crashes are extremely unlikely. Stars are tiny compared with the immense distances between them, so even when galaxies pass through one another, most stars continue untouched on purely local scales. Yet the galaxies themselves can be dramatically distorted. Gravity works on the larger structure, stretching disks, twisting spiral arms, and throwing stars into vast new orbits. So the violence of a merger is real, but it happens through changing gravitational choreography rather than countless head-on stellar impacts. This makes galaxy collisions feel even stranger. A galaxy can be wrecked without most of its stars ever hitting anything. Its shape, motion, and future can be altered completely, while individual stars remain physically intact. The universe often works that way on great scales. The damage is structural, not granular. In a future Milky Way and Andromeda encounter, the familiar forms will be torn apart, even though most stars will simply be redirected through a new cosmic dance. New streams of stars will spill into the space between galaxies. As large galaxies interact, gravity can draw out long tidal features made of stars, gas, and dust. In the future meeting between the Milky Way and Andromeda, new streams of stars are expected to pour outward into the surrounding space, creating luminous arcs and tails that could extend across enormous distances. These features will not be mere decoration. They will be the visible evidence of a major gravitational rearrangement, showing where stars have been pulled from their old homes and cast into wider orbits. Some may later fall back inward. Others may remain in extended halos or in intergalactic regions for immense spans of time. The sight would be extraordinary. Instead of two separate spiral galaxies facing one another, the local universe would display sweeping rivers of stars connecting and surrounding them. Intergalactic space would become laced with starlight. The darkness between galaxies would no longer be mostly empty. It would be illuminated by the very material their encounter had torn loose. Future astronomers may watch a very different night sky unfold. If intelligent observers exist in the far future during the Milky Way and Andromeda encounter, their sky may look astonishingly different from ours. Andromeda, now a faint patch to human eyes, will grow larger over hundreds of millions of years, eventually swelling into a dominant structure across the sky. Later, tidal distortions, star streams, and rearranged galactic light may create a night far richer and stranger than the one we know. The familiar Milky Way band could change shape. Great arcs of stars might appear where none exist now. The cosmic calm we inherit would be replaced by a visible reminder that galaxies evolve on long timescales. This thought gives astronomy a personal dimension. The sky feels permanent to us, yet it is only one chapter in a much longer visual story. Future observers may live beneath a far more dramatic heavenscape, where our present sense of the galaxy as a stable home has been replaced by a slowly unfolding spectacle of merger and transformation. Some dwarf galaxies are mostly dark matter with very few stars. Among the strangest galaxies known are tiny dwarf systems, whose visible stars seem almost like an afterthought. Their motions suggest that they are dominated by dark matter, with only a sparse population of stars lighting up a much larger invisible mass. These galaxies can appear faint and insubstantial, yet their gravity reveals something much deeper and heavier holding them together. That makes them some of the best natural laboratories for studying dark matter on small scales. They are also haunting objects in their own right. Imagine a galaxy that is mostly present in gravity and only faintly present in light. A few stars drift within it, but the real substance is hidden. Such dwarfs remind us that not every galaxy is a bright spiral or a crowded cluster of suns. Some are dim, fragile-looking things whose importance far outweighs their appearance. Intergalactic space around large galaxies may be filled with these quiet companions, each one a luminous hint of a much darker underlying structure. Others may be slowly dissolving into intergalactic streams. Not every dwarf galaxy survives intact. Some venture too close to a larger neighbor and begin to come apart under tidal forces, losing stars and gas little by little until the whole system stretches into a stream. This can happen so gradually that the process feels almost like melting rather than destruction. A once distinct galaxy becomes elongated, thinned, and eventually hard to recognize as a single bound object. Its stars continue moving, but now as part of a larger intergalactic feature rather than a compact home. These dissolving dwarfs reveal galaxy evolution in real time on the vast, slow clock of the universe. They also show how large galaxies grow through quiet consumption. The remnants do not vanish. They become trails, arcs, and diffuse additions to the halo and surrounding space of the larger system. Intergalactic space, in this sense, becomes a graveyard and a memory field, holding the stretched remains of small galaxies that are no longer whole but not yet fully forgotten. Tidal tails can stretch longer than the galaxies that made them. When galaxies interact, gravity can pull out spectacular tidal tails, elongated streams of stars and gas thrown far from the main bodies of the galaxies involved. These tails can become so extended that they rival or even exceed the visible size of the galaxies that produced them. That is part of what makes them so breathtaking. A compact galactic encounter can create structures of extraordinary reach, flinging material outward into graceful arcs that seem almost too delicate for the violence behind them. Tidal tails are more than beautiful signatures. They preserve the dynamics of the encounter, revealing how strongly the galaxies pulled on one another and how material responded to that pull. In some cases, clumps within these tails may even become sites of future star formation. So a tail is not merely debris. It is both record and possibility. Intergalactic space can become decorated with features longer than the galaxies themselves, ridden by gravity and lines of stars and gas. Tidal bridges can briefly connect galaxies across the dark. Sometimes an encounter between galaxies does not only pull material outward into tails. It can also build a bridge, a stretched lane of stars and gas, linking one galaxy to another for a time. These tidal bridges are temporary structures, yet they can appear as if the galaxies are physically joined across the darkness. The image is stunning. Two stellar systems that once seemed separate become connected by a luminous thread drawn out by gravity. Such bridges can transport gas, trigger star formation, and reveal the geometry of the encounter in a particularly dramatic way. They are like fleeting causeways across intergalactic space, built not by intention, but by motion and force. What makes them especially evocative is their impermanence. The connection is real, but it does not last forever. Over time, the structure disperses or is reabsorbed. For a while, though, the dark between galaxies is crossed by a visible link, as though gravity itself had reached out and tied them together. Gas stripped from galaxies can seed future star formation elsewhere. When gas is torn from a galaxy during an encounter, or while moving through a dense cluster environment, it does not always remain a useless cloud. Under the right conditions, that displaced material can cool, condense, and help form new stars in places far from the galaxy that originally held it. This gives intergalactic space a surprising fertility. Matter lost in one setting can become the raw ingredient for creation in another. Imagine gas removed from a spiral arm by tidal forces or pressure, then gathering later into clumps where new stars ignite. The parent galaxy may have been rogged, yet the stolen material has not lost its future. It has merely changed location. This is one of the most beautiful examples of cosmic recycling. Space between galaxies is not only the site of loss. It can also become a nursery where stripped gas begins a new chapter. Matter in the universe is rarely wasted. It is moved, reshaped, and given another chance to shine. Intergalactic space can recycle matter from dead galaxies into new ones. Galaxies do not live forever in the forms they begin with. Some are stripped, disrupted, or merged into larger systems, losing stars, gas, and heavy elements to the wider environment. Yet that material does not simply disappear. It can linger in halos, streams, and diffuse intergalactic reservoirs until gravity draws it into new structures. In this way, matter from one galaxy can later help nourish another. The universe is full of inheritance. A galaxy may contain gas enriched by stars that lived and died in an older system long ago. Heavy elements forged in ancient suns can be carried outward, mixed into the intergalactic medium, and eventually folded into fresh clouds where new stars and planets form. This gives cosmic history a remarkable continuity. Death in one place becomes possibility in another. The dark between galaxies is part of that exchange. It is the medium through which material can be transferred, stored, and eventually reborn in forms that would never reveal their ancestry at first glance. Entire stellar nurseries may form in material thrown between galaxies. The space between interacting galaxies can sometimes do more than hold debris. It can become a place where giant star-forming clouds take shape. Gas compressed in tidal tails or bridges may gather into dense pockets, and once those pockets become cold and thick enough, star birth can begin. That means a region produced by galactic upheaval can transform into an actual stellar nursery, lighting up with young hot stars far from any galactic center. The idea is thrilling because it turns what sounds like wreckage into a cradle. The matter flung outward during an encounter does not always remain a fading trail. It can become active, luminous, and generative. These nurseries reveal that intergalactic space can briefly host conditions we usually associate with the disks of galaxies. Gravity, compression, and cooling combine to create new light in an unexpected place. The universe keeps refusing simple categories. What begins as damage can become birthplace, and the darkness between galaxies can suddenly bloom with stars. Some stars are born far from any galactic center. We often imagine stars forming deep inside galaxies, in spiral arms, dense clouds, or busy star-forming regions near the main stellar body. Yet not all stars begin life there. In interacting systems, compressed gas in tails, bridges, and stripped clouds can ignite star formation far from any galactic center. These stars may arise in remote pockets of matter cast into intergalactic space, giving them an origin more isolated than the familiar crowded nurseries inside galaxies. That changes the emotional feel of star birth. A star does not always need a grand galactic city around it. Under the right conditions, it can emerge in a comparatively lonely outlying region, lit by the consequences of some earlier gravitational encounter. Such stars carry the history of motion and disruption in their birthplace. They are reminders that the universe can create in peripheral places. The dark beyond galaxies is not only a zone of drifting leftovers. It can also be a place where entirely new suns begin their long careers. Intergalactic star clusters can drift where no great galaxy rules. Not every gathering of stars between galaxies is a loose stream or a single wanderer. In some cases, compact star clusters may also exist in intergalactic space, either stripped from galaxies or formed in tidal debris during interactions. These clusters are especially intriguing because they preserve companionship in exile. A star cluster drifting between galaxies is not a full galaxy, yet it is also more than a solitary object. It is a small community of stars traveling through a realm with no dominant galactic center nearby. Such clusters may survive for long periods if their stars remain gravitationally bound strongly enough. Their existence would show that intergalactic space can host not just diffuse material, but structured stellar systems with their own local order. The image is wonderfully strange. A cluster of suns, perhaps ancient or perhaps born in tidal chaos, moving through the dark without allegiance to any major galaxy. Even between the great star cities, smaller islands of starlight can still endure. Space between galaxies is a place of loss and creation. If there is one theme that runs through all these intergalactic stories, it is transformation. The darkness between galaxies is where stars can be torn from their homes, where dwarf galaxies can unravel, where gas can be stripped and scattered, and where tidal structures can stretch across enormous distances. Yet it is also where new stars may form, where recycled matter can begin again, and where fresh structures can briefly emerge from the aftermath of collision. This dual nature makes intergalactic space feel almost alive with consequence. It is not simply the empty interval between more important places. It is one of the universe's great zones of exchange, where endings and beginnings share the same stage. A galaxy can lose material there, and another system or new generation of stars can gain it later. In human terms, we might call that destruction and renewal. In cosmic terms, it is simply how matter keeps moving, changing, and finding new ways to shine in the dark. There may be faint galaxies we still miss in intergalactic gloom. For all our great surveys and brilliant telescopes, the universe may still be hiding entire galaxies simply because they are too faint, too diffuse, or too easily lost against the darkness around them. We tend to imagine galaxies as bright spirals or glowing ellipses, but nature is under no obligation to make them easy to spot. Some may contain only a modest number of stars spread thinly across a wide region, producing so little surface brightness that they almost dissolve into the background. Others may lie in awkward positions, half buried in glare from brighter neighbors or masked by foreground structure. This means intergalactic space may not be as fully charted as it seems. There could still be dim stellar islands out there, drifting quietly in the dark, unnoticed, not because they are unimportant, but because they whisper instead of shine. The cosmic map still has room for hidden settlements, waiting for deeper eyes and better patience to finally bring them into view. Some galaxies are so diffuse they almost vanish into the dark. Not every galaxy announces itself with brilliance. Some are so spread out that even when they contain many stars, their light is diluted across such a broad area that they become hard to see at all. These ultra-diffuse galaxies can be enormous in size, rivaling the Milky Way in diameter, yet appear ghostly and weak because their stars are scattered thinly like embers across a fog. They are some of the strangest cities in the universe, vast but dim, present but nearly invisible. What makes them especially fascinating is how they challenge intuition. We expect something large to be obvious. Instead, these galaxies hover at the edge of detectability, revealing that size and visibility are not the same thing in the cosmos. Some may survive because dark matter helps hold them together despite their sparse starlight. They are like faded fingerprints left in the dark, proof that the universe can build entire galaxies that almost erase themselves from sight. Invisible matter shapes intergalactic space more than visible matter does. If we judged the universe by what shines, we would misunderstand most of it. Visible matter, stars, gas, glowing galaxies is only part of the story. The deeper architecture of intergalactic space is shaped even more strongly by dark matter, the unseen mass whose gravity dominates large-scale structure. It is dark matter that helps determine where filaments form, where galaxies gather, and where the great hollows of the cosmos open out. Ordinary matter follows its pull, settling into the deeper gravitational valleys already laid down by something we cannot directly observe. This is one of the most profound reversals in modern science. The luminous universe is not the master structure. It is more like the illuminated trim on a hidden framework. Intergalactic space, which seems like the realm of almost nothing, is in fact deeply governed by something invisible. The roads, walls, and gathering places of the cosmos owe more to unseen mass than to the glowing objects that first catch our attention. Most of the galaxy cluster's mass cannot be seen directly. A galaxy cluster is one of the most massive structures bound together in the universe. Yet most of its mass does not appear in stars, galaxies, or even the hot gas glowing in X-rays between them. The majority is dark matter, present through gravity but absent from ordinary sight. This means that when we look at a cluster, we are seeing only part of the whole. The visible galaxies are dramatic, and the intergalactic gas is substantial, but neither accounts for the cluster's true mass budget. The hidden component outweighs them both. That fact changes the mood of observation. A cluster is not just a bright congregation of galaxies in a shared atmosphere. It is also a vast unseen scaffold whose gravity binds the entire system together. Without it, the visible parts would not behave as they do. So the grandest crowded regions of intergalactic space are governed mainly by something no human eye could ever directly behold. Gravitational lensing reveals hidden mass between distant galaxies and us. One of the most beautiful tricks in astronomy comes from gravity itself. When a massive object lies between us and a more distant source, its gravity can bend the path of light, distorting and magnifying what lies behind it. This effect is called gravitational lensing, and it allows astronomers to detect mass that does not shine. If the visible matter in the foreground were all that existed, the lensing would be weaker than what is observed. The extra bending reveals hidden mass, often in the form of dark matter spread through clusters and intergalactic space. In this way, gravity becomes a kind of ink, showing where the invisible resides by how strongly it curves the light passing through. What makes this so captivating is that it turns the universe into its own measuring device. Intergalactic space does not merely separate us from distant galaxies. It contains mass that can warp their appearance, exposing what cannot otherwise be seen. Intergalactic space can bend light like a giant transparent lens. A glass lens bends light because of its shape and material. Intergalactic space bends light for a stranger reason. It contains mass, much of it dark, and mass curves space-time. When light passes through a region threaded with enough matter, especially near clusters or massive structures, its path can be deflected. The space itself becomes a lens, though one with no visible edge and no polished surface. This is one of the most magical-sounding realities in cosmology. The darkness between galaxies can act like a transparent optical instrument, warping and focusing the light of more distant objects. Sometimes the effect is subtle, producing slight distortions in galaxy shapes. Sometimes it is dramatic, creating arcs, multiple images, or strong magnification. Either way, the lesson is the same. Intergalactic space is not passive emptiness. It has weight, geometry, and influence. Even where nothing obvious appears to be present, the universe can still bend light with the slow, invisible strength of gravity. One cluster can magnify galaxies lying far behind it. A massive galaxy cluster can become a natural telescope. Its enormous gravity bends and focuses the light of more distant galaxies behind it, making some of them appear brighter, larger, or stretched into luminous arcs. This magnification is not a small curiosity. It can allow astronomers to study galaxies that would otherwise be too faint to detect at all. In effect, the cluster lends us a stronger view of the deeper universe. What makes this especially thrilling is that the lens itself is alive with complexity. The distribution of galaxies, gas, and dark matter inside the cluster determines how the magnification works, producing regions of stronger and weaker amplification. The result can be both scientifically useful and visually astonishing. A foreground congregation of galaxies, already vast in its own right, becomes an instrument that reveals even more distant realms. Intergalactic space does not only hide the remote universe. Under the right conditions, it helps us bring that remote universe closer. That magnification lets us glimpse worlds otherwise beyond reach. Many of the faintest and most distant galaxies in the universe are simply too dim for easy observation, even with powerful telescopes. Their light has traveled for immense spans of time and spread across expanding space until only a fragile trace remains. Gravitational magnification can change that. When a massive foreground structure amplifies their light, galaxies that would otherwise remain beyond our reach can suddenly enter the realm of study. This is one of astronomy's most moving abilities. By using the gravity of intervening matter, we can sometimes see farther back and deeper than our machines alone would allow. Objects that would have stayed hidden become visible enough to analyze, revealing their shapes, their star formation, and their role in early cosmic history. The effect feels almost generous. The universe places a lens in the foreground, and through that lens lets us glimpse worlds we could not otherwise touch with observation. Intergalactic gravity becomes a bridge to the almost unreachable. Some of our best views of the early universe use intergalactic gravity. When astronomers want to study some of the earliest galaxies, they do not rely only on bigger mirrors and more sensitive detectors. They also make use of nature's own lenses. Massive structures in intergalactic space, especially galaxy clusters, can magnify light from ancient background galaxies that formed when the universe was still young. Without that help, some of those objects would be far harder to study. This gives intergalactic gravity a remarkable role in modern astronomy. It is not only something to measure, it is something to use. A cluster in the foreground can help reveal star systems from a much earlier age, allowing us to see formative stages of cosmic history more clearly than we otherwise could. In that sense, the deep universe sometimes comes into focus through the very structures that lie in the way. The darkness between galaxies becomes part of the observing process, turning gravity itself into one of our best tools for looking back toward the dawn of structure. The darkness between galaxies can help us see farther. At first, this sounds backwards. Darkness seems like the enemy of sight, the very thing that hides distant wonders from us. Yet in cosmology, the space between galaxies can help reveal the deeper universe. It does this through gravity, through lensing, and through the relative transparency that allows ancient light to cross enormous distances. The great dark stretches of intergalactic space are not always obstacles. Sometimes they're what make deep observation possible. They preserve the long paths light must travel. They contain the massive structures that magnify remote galaxies. They hold the clues that let astronomers decode what happened across those immense journeys. This gives darkness a surprisingly active role. The void is not just what separates us from distant things. It is part of what lets those distant things be seen at all. In the universe, seeing farther often depends on understanding the dark in between, because the darkness itself shapes the messages that finally reach our telescopes. Future telescopes may map the cosmic web in stunning detail. Right now, much of the cosmic web is known through indirect traces, large surveys, and partial glimpses. But future observatories may reveal it with far greater richness, showing how gas, galaxies, and dark matter line up across intergalactic space in ways that are much more detailed than today's maps. Better X-ray missions, sharper radio arrays, deeper optical surveys, and new techniques for tracing faint gas may all contribute to a more complete portrait. What is exciting is not just the promise of prettier images. It is the possibility of finally seeing the universe's large-scale scaffolding as a vivid connected system rather than a partly inferred one. That could transform how people imagine the cosmos. Instead of isolated galaxies floating in darkness, The web itself may become familiar, a grand visible pattern of filaments, knots, and hollows. Intergalactic space would stop seeming blank to the public imagination and start looking like what it truly is, one of the richest structural environments in existence. Astronomers are still hunting the faintest filaments between galaxies. Some of the cosmic web has already been traced, but its faintest strands remain elusive. These filaments can contain diffuse gas spread across immense distances, glowing so weakly or absorbing so subtly that they are extremely hard to detect. Astronomers continue to search for them using sensitive instruments, clever observing strategies, and the light of distant background sources. The work has a certain romance to it. It is a hunt for structure that almost refuses to show itself, threads of the universe so delicate they hover at the edge of visibility. Yet those faint filaments matter enormously. They may carry large amounts of ordinary matter, guide the growth of galaxies, and connect the brightest nodes of the cosmic web. Finding them is like finding the hidden stitching in a vast fabric. The luminous objects are easier to notice, but the finer threads are what truly reveal the weave. Intergalactic space still contains structures that science is only beginning to chase into view. We have never directly seen most intergalactic matter with our eyes. Much of what fills the space between galaxies does not present itself in a form human eyes could ever naturally observe. Some of it glows in X-rays, some reveals itself only through absorption lines, and some is known mainly from its gravitational effects. Even with telescopes, much of the intergalactic medium is not something we simply photograph in the ordinary sense and admire in visible color. That fact is worth sitting with because it shows how much of cosmic reality lies beyond everyday perception. The darkness between galaxies is not mostly understood through straightforward seeing. It is reconstructed through clues, instruments, and inference. We know it is there, but often not because it shines in any familiar way. This gives the subject an added wonder. The universe's great connective tissue exists largely outside the range of unaided human experience. We have come to know it by building new senses, extending sight beyond eyes, and trusting evidence that reveals what visible light alone cannot. Much of intergalactic space is known through traces, not pictures. Astronomy often rewards us with lovely images, but the deeper truth behind intergalactic space is frequently pieced together from traces rather than scenic views. A slight absorption in a quasar spectrum, a distortion in background galaxy shapes, a faint X-ray glow, a radio signal from accelerated particles. These are not always the kind of evidence that becomes a simple picture on a poster. Yet together they build one of the richest portraits in cosmology. This is part of what makes the field feel almost detective-like. Astronomers read clues left in light, gravity, and motion to reconstruct an environment that is too diffuse, too dark, or too energetic for ordinary imaging alone. Intergalactic space in this sense is one of the great inferred landscapes of science. It is real, measurable, and structured, but often known through its effects more than through direct appearance. The universe leaves signs before it leaves pictures, and scientists have learned to read those signs beautifully. The quiet between galaxies may decide how galaxies live or die. It is tempting to think a galaxy's fate is determined mainly by what happens inside it, by its stars, its black hole, or its own internal gas. Yet the wider intergalactic environment may be just as important. A galaxy's access to fresh gas, its encounters with neighbors, the pressure of surrounding plasma, and the pull of large-scale structure can all influence whether it keeps forming stars, loses its fuel, or becomes dormant. In other words, the conditions in the surrounding darkness may decide whether a galaxy grows, transforms, or slowly fades. This is one of the deepest shifts in how modern astronomy sees the universe. galaxies are not sealed biographies. They are open systems shaped by context. The quiet space around them is not merely background. It can starve them, feed them, strip them, or guide them into new interactions. Intergalactic space may therefore be one of the hidden authors of galactic destiny, shaping lives on scales far beyond the stars within any single system. Intergalactic space controls what galaxies can feed on next. Galaxies need gas if they are to keep making new stars. That gas does not arise from nowhere. Much of it must come from outside, drawn inward from halos, filaments, and the broader intergalactic medium. This means the space around a galaxy acts almost like a pantry, though one that can be full, depleted, heated, or disturbed, depending on the environment. A galaxy in a rich filament may have access to incoming streams of fuel. A galaxy in a hot, dense cluster may find its gas stripped or prevented from cooling. The difference can alter its future for billions of years. This makes intergalactic space feel unexpectedly intimate. The great darkness between galaxies is not only a large-scale structure. It is part of how galaxies eat, grow, and continue their cycles of star birth. A galaxy's next generation of suns may depend less on what it already contains, and more on what the surrounding cosmic environment is willing, or able, to deliver. To understand galaxies, we must understand the darkness around them. For much of astronomy's history, galaxies themselves took center stage. Their spirals, halos, bulges, and black holes seemed like the obvious places to focus. But the more we learn, the clearer it becomes that galaxies cannot be fully understood in isolation. Their growth, interactions, fuel supply, and large-scale arrangement all depend on the intergalactic environment around them. The darkness is not empty stage scenery. It is part of the mechanism. Filaments guide where galaxies gather. Gas reservoirs influence whether they keep forming stars. Cluster environments can strip and transform them. Dark matter sets the underlying structure from the beginning. This means a galaxy is only half the story if we ignore the space around it. To know why a galaxy looks and behaves the way it does, we must ask what larger web it belongs to and what conditions surround it. The stars may be the visible actors, but the darkness between galaxies often writes the script they live by. The greatest structures in existence are mostly built from mere nothing. This may be the most astonishing idea of all. The largest structures known in the universe, the vast filaments, superclusters, and connected patterns stretching across incomprehensible distances, are built from material that is often so thinly spread it almost feels like nothing at all. Intergalactic gas can be extraordinarily sparse. Dark matter cannot even be seen directly. Yet together they create the framework of the cosmos. The result is a universe whose grandest architecture is not made from dense walls or blazing solid forms, but from near emptiness shaped by gravity over time. That changes how we imagine scale and substance. Greatness in the universe is not always about richness in the local sense. Sometimes the largest designs arise from the faintest ingredients, patiently arranged across immense distances. Intergalactic space proves that almost nothing, given enough room and enough time, can become the basis for the biggest structures nature has ever made. Intergalactic space is where the universe becomes vast beyond intuition. There are many places in astronomy that feel large, but intergalactic space is where scale begins to defeat ordinary thought altogether. Inside a solar system, distances are immense but still somewhat graspable. Inside a galaxy, they become more abstract. Between galaxies, especially across clusters, filaments, and voids, the mind starts to lose its grip. Light travels for millions of years. Structures span realms so wide that familiar comparisons begin to fail. Yet this is also where the universe reveals its fullest grandeur. The great web, the hidden matter, the shared gas, the lensing, the expansion. All of it becomes most striking in the space between galaxies. This is the domain where the cosmos stops feeling like a collection of objects and starts feeling like a vast evolving architecture. Intergalactic space is not only big, it is the place where bigness itself changes character, becoming something more like awe than measure, more like wonder than number. The emptiness between galaxies may be one of nature's richest frontiers. At first glance, the space between galaxies sounds like the least promising frontier imaginable. It seems like a region defined by absence, darkness, and thinness. Yet nearly every deeper look has made it richer. It holds missing ordinary matter. It preserves the cosmic web. It records ancient transitions in the young universe. It channels the growth of galaxies. It bends light. It hosts wandering stars, displaced gas, magnetic fields, fast particles, and the lingering influence of black holes and mergers. Even now, much of it remains difficult to map in full. That makes it one of nature's most exciting frontiers, not because it is crowded with obvious spectacle, but because it keeps turning apparent emptiness into revelation. The more astronomy advances, the more this dark realm grows in importance. What once seemed like a blank interval between more interesting objects now looks like one of the great hidden domains of reality. The emptiness was never empty. It was waiting to be understood. And now we've reached the quiet edge of our journey through intergalactic space. Tonight, we drifted far beyond the bright islands of galaxies and into the immense darkness between them. We wandered through the hidden gas that fills the cosmic web, past vast filaments stretched across the universe, and beside voids so enormous they seem almost impossible to imagine. We passed wandering stars with no true home, rogue worlds lost in the dark, and giant clusters wrapped in blazing halos of unseen heat. We followed ancient light crossing unimaginable distances and glimpsed the way gravity can bend that light, turning the darkness itself into a lens. And perhaps that is the strangest and most beautiful part of all. What first sounds empty is not empty at all. The deep spaces between galaxies are filled with motion, memory, structure, and quiet transformation. Even there, matter gathers. Light travels. Galaxies feed, collide, and change. Even there, the universe is busy becoming itself. So now, as your thoughts begin to slow, you can let that great cosmic darkness become something softer. Not a cold emptiness, but a wide and peaceful expanse. A place where distant rivers of stars drift in silence, where ancient light glides on, and where the universe stretches around you without hurry. If you enjoyed this journey, I'd love for you to like, subscribe, or leave a thought below. It helps more sleepy listeners find their way here. And if you happen to still be awake, there's another video waiting for you on the screen now, ready to carry you onward into one more world of wonder. But for now, let your breathing slow. Let your body grow heavy, and let the vastness of the cosmos fade softly into rest. Sleep well, and good night.